Imagine you're going to a park to play baseball with a few of your friends. When you get to the park, you suddenly realize that you forgot your ball glove. Thankfully, one of your friends offers for you to borrow one of their extra gloves. However, as you go to put it on, you realize that they're right-handed, you're left-handed, and your hand doesn't fit into that ball glove. Our hands are very similar in their structure and function, and yet you can have one hand that doesn't fit into the glove that's made for the other hand. This is because, of course, even though they're very similar, they are mirror images of each other, right? So no matter how I try to match my hands together, I can't superimpose them on one another, or they don't completely overlap. And so they're, of course, unique hands. We have our right hand and our left hand. In organic chemistry, we have the same kind of scenario with molecules. Our molecules can be right-handed and left-handed, and they can be unique structures just based on that change. We refer to this as enantiomers. So enantiomers are molecules that are mirror images of each other. That are non-superimposable. Now, in order for two molecules to be enantiomers, they have to be mirror images, but they also have to be asymmetrical or chiral. If we compare just two hydrogen atoms, so they both are symmetrical spherical shapes, and even though these, of course, are mirror images of each other, they can be superimposed over each other, they perfectly overlap, and so there's nothing different between these two hydrogen atoms. In order to have a chiral molecule, we need asymmetric molecules. If we look at these two molecules here, we see that they are, again, mirror images of each other, right? So I'm holding them, I have my molecule on my right and on my left, and you can see they're exactly mirroring each other. Now, as we look at these molecules, so we have our carbon, of course, in the middle. We have the white ball representing our hydrogen. We've got the green representing our chlorine, brown representing iodine, and orange representing bromine. So we have four different groups attached on here. And as we take our mirror image molecules, we can rotate them around and try to superimpose them on one another. So you can see my green chlorines overlap, my bromine and carbons overlap. But, of course, I don't have my overlap over here. And no matter how I try to rotate these, I can't get them to completely overlap and superimpose on each other. So these are two mirror image or enantiomers of each other. They can't be superimposed over one another. Now, in order to do this, I need to have these four unique groups attached to one carbon atom. Here I have the same molecule represented using our wedge dash notation. Again, the wedge means the bond is coming out towards me, the dash means the bond is going away from me. This gets my nice tetrahedral shape, and I again have my very asymmetric structure here. So this carbon here I refer to as a chiral center, since it's the center of my asymmetrical structure, and I would refer to this as a chiral molecule overall, because we have this chiral center with these four unique groups attached. As long as we have our chiral center, we'll normally have a asymmetrical molecule that will then have two different unique enantiomers. Now, what if we compare two molecules that don't have four unique groups attached to a central carbon atom? So here we have still our tetrahedral carbons with four things attached, but we have two identical hydrogens attached to each of these molecules. Now notice again, these are perfect mirror images, but as I rotate this around, you can see they perfectly overlap or superimpose over each other. So even though I've created two mirror images, they overlap, and so they aren't actually different molecules or different enantiomers. So if I don't have four unique groups attached, I can't have enantiomers, and I just have those mirror images as the identical molecule. So again, I have my molecule represented here using wedge dash notation. With only 3 unique groups attached, this becomes achiral. With an achiral molecule, I'll always have no possible enantiomers. And so I really only have my one isomer, right? There's no other way that I can rearrange that to create a unique mirror image, since I don't have that asymmetry that is associated with my chiral molecule up here. Now, once we've identified a chiral molecule, so we've found that carbon atom, and we've seen that we have 4 unique groups to 1 carbon, we know that we're going to have 2 different enantiomers of that molecule. So here I have my 2 enantiomers shown here. You can see how they're perfectly mirrored right across this dotted line that I have here. And again, of course, I could try to rotate that, but I'd never be able to get it to superimpose over my other molecule. Now, since I have these 2 unique structures, these mirror image structures, I also need a way to identify which enantiomer I have. So I'm going to need a new naming system in order to tell me what my enantiomer is. So what we're going to use for naming these is our RS notation. So one of our enantiomers is going to be designated as R, the other one will be designated as S. We're going to have a very specific way of determining which one is the R or the S enantiomer, so that we can use our structure to determine the name, and use the name to determine the structure, as always is our goal in organic chemistry. So we'll use a series of rules in order to determine what notation our enantiomer is. The first thing that we're going to do is we're going to prioritize our groups based on their atomic numbers. So I'm going to come over here to my structure, and I'm going to give the highest priority, so I'll give a little 1 by the atom that has the highest atomic number. So that would be my iodine first, that gets a little 1. My bromine would be number 2. My chlorine would be number 3. And my hydrogen would be number 4. So I'm just ranking them highest to lowest atomic number. My highest is my iodine. My lowest is my hydrogen. Now, if I consider a slightly more complicated molecule, like the enantiomer is shown below here, I am still going to assign my priority based on the atomic numbers. So in this case, chlorine has the highest atomic number and be number 1. But now when I go to look at my next highest priority group, you'll notice that I have 2 carbons here. Now you might initially think, well, 2 carbons aren't unique, so therefore this should be achiral or symmetrical. But we need to consider the whole group, not just that one atom that's directly bonded to my carbon. So even though my 2 carbons are the same that are attached to my central carbon, they each look differently because they have other things that they're connected to besides their initial bond, right? So over here I have this group that's 2 carbons. Over here I have this group that's just a single carbon. So this group is unique from the group on the left, and it still is a chiral center. But in terms of ranking priority, if I'm ranking based on atomic number, 2 carbons, of course, have the same atomic number. So in this case, what I have to do is I have to break the tie by looking at what's connected to that carbon. Right? So the carbons are both tied at 2, and then we go to that carbon and consider what's attached there. So this carbon has another carbon and 2 hydrogens. So I'll write that down. It's carbon, hydrogen, hydrogen is the 3 things attached here. Whereas this carbon has hydrogen, hydrogen, and hydrogen attached here. Since my carbon over here has a higher atomic number compared to my hydrogen, I'm going to give this group the higher priority, and I reduce this to my 3rd priority. So what we do is we look for the first point of difference If our groups are tied in terms of an atomic number, we'll move down and look at what's bonded to that next atom. And we'll keep going until we find a difference between the two groups. So this group is higher priority because it's attached to the group that has a higher atomic number. This gets lower priority, and hydrogen, as before, gets our lowest priority overall. Once we've determined the priority of our groups, we're going to rotate our structure to put the lowest priority group in the back. The easiest way to do this rotation is using a molecular model system. So here I have my enantiomer built here using my molecular models. I'm going to take my hydrogen, which is my lowest priority group, as I just determined here, and I'm going to turn that so it points to the back. So now I can see my molecule with my hydrogen pointing directly backwards. And what we're going to do is we're going to look at our other groups. We're going to start at the highest priority group, that's my iodine over here, and we're going to move to the next priority group. So I move over here to my bromine, and then we're going to keep following in sequence towards each of our groups. So highest priority, second, third priority. Notice as I'm doing that, I'm moving my hand in a counterclockwise direction. You see that movement there? So that means that this is a S notation. S denotes counterclockwise, R denotes clockwise. R, you'd be rotating to the right, so that we refer to as that would be clockwise. S is rotating to the left, and that becomes counterclockwise. So the RS comes from Latin. R is for rectus, which means right. S is for sinister, which means left. It's just that rightward rotation or leftward rotation that we get with clockwise or counterclockwise. Now that I've determined the notation of my enantiomer over here on the right using my molecular model, I'm going to determine the notation of my enantiomer here on the left just using drawings on my marker board. So this is an important thing to practice as well, since we don't always have molecular models that we can work with. Now right off the bat, I'll give you a quick shortcut. If we have two pairs of enantiomers, if one is S, the other one is always going to be R. Right? So whenever something is mirrored, S turns into R. So that's the quick way to determine what this enantiomer is, if we already knew what its mirror image was. But we'll go ahead and do it the long way using our three rules as well. So first, let's prioritize our groups. So again, our priorities are going to be the same as our other enantiomer. Iodine is the highest priority, then bromine, chlorine, and hydrogen. Now I need to rotate my molecule to put the lowest priority group, of course that's my hydrogen, in the back. So here I need to envision picking up my molecule and flipping it around like a pancake and putting it back down. So I'm going to draw my carbon, of course, is going to stay in the center since I'm just picking it up and flipping it around. My chlorine doesn't move either, right? It's just picked up, put back down in the same spot. The main changes occur down here. My iodine on the left gets picked up, and it's going over onto the right side. So you see how my thumb moves like the iodine would move over to the right. And my bromine and my hydrogen are both going to move over to the left as they're flipping around. Now my bromine was pointing back away from me. Now since it's flipping around, it's going to be pointing towards me. So my bromine ends up on the wedge coming out towards me. My hydrogen was coming out towards me. Now it's going to be flipping over and pointing away from me. So I put my hydrogen on the dash, going away from me over here. Now I'll just quickly rewrite my priorities. 1, 2, 3, 4. We can also redraw this in sort of a half Newman projection. So remember the Newman projection, we replace our carbon atom with a circle representing the bond from our carbon back towards the other carbon. In this case, we're going to build our little Newman projection looking along this bond here. So my hydrogen I'm just kind of hiding as my low priority group. My chlorine's coming out the top, iodine on the right, and bromine on the left. So both of these are acceptable ways to draw this. The half-Newman projection can be helpful because it gets that hydrogen out of the way since we're not going to use it for our third step. Now the third step, of course, is to move from our highest priority group to our lower priority group. Again, I'm ignoring my hydrogen here. And notice I'm moving in a clockwise direction. So a clockwise rotation, that is rotating to the right, or my R notation. So I'm confirming again that this is my R enantiomer, which I already knew since it was the mirror image of my S enantiomer. Enantiomers are specific examples of what we call stereoisomers. So stereoisomers are any kind of isomer that differs not in terms of where our atoms are connected or what atoms are connected to each other, but just a spatial 3D kind of difference in how our atoms are positioned in our molecule. Right? So if we compare our two enantiomers here, they still have all the same bonds and all the same connections. Right? We still have that bromine attached to my carbon, the iodine and the chlorine all attached to that same carbon. So we haven't changed any bonds, we've just changed the relative spatial positioning of those bonds. Now again, as we mentioned with our hand, the example of our hands look the same structurally, right? They have very similar properties. They both have 4 fingers and 1 thumb. But what they have that's unique is a unique shape based on that different spatial arrangement of our atoms. And again, with our hand, that meant that our right hand doesn't necessarily fit into a glove that's designed for our left hand. And this has the same kind of effect in biological systems with our organic enantiomers. Right? A molecule that has the S notation is not necessarily going to fit with a molecule that's expecting the R notation. And so it can actually affect the interactions between our molecules, and it can have a huge effect in our biological systems. Often our biological systems are expecting specific enantiomers, and the wrong enantiomer either doesn't work or might actually cause problems just based off of that slight difference in the shape. So as we'll see, it's going to be very important that we can distinguish between our enantiomers. We can do this again using our names. And as we'll see, we're also going to need ways to measure what enantiomers we have and distinguish between these, if just from the molecule as well as from the name.